Hello, welcome back to the COVID-19 inspired video series for Mr. Billingham's Honors Precalculus class. This is the sixth video for Chapter 10 and we'll cover the second half of Section 10.2. Some of the sections we'll be looking at involve stem and leaf plots, frequency tables, modes, and symmetry. A quick way to organize and display a small set of numerical data is with a stem plot, also called a stem and leaf plot. Each number in the data is split into a stem, consisting of the initial digit or digits, and a leaf, which is the final digit. Let's take a look. In Table 10.3, we see for each state the percentage of state residents in 2010 who are 65 or older. It's a fairly difficult table in its current format to get much sense of. So let's talk about how we build a stem and leaf plot. Looking through the table, we see only a single entry beginning with 7 for Alaska, 7.7. So we enter a leaf of 7 for that. There are no entries that begin with 8, so we make sure to keep the 8 because that reminds us no percentages started with 8. Let's look for 9s. The only 9 is for Utah, and it's 9.0, so next to 9 we write a 0. Now we look for 10s. For percentages beginning with 10, we have 10.3, 10.7, and 10.9. So I enter that as 3, 7, and 9. I try to keep my spacing equal. If I do this carefully, I can do a complete stem and leaf plot for the data in Table 3, and the result will look like this. So we can see in this a number of things that we'll explore in just a moment, but one of the key ideas is to keep the leaves evenly spaced so that a row with twice as many leaves will appear twice as long. Exploration 1 has a number of questions that we can answer from the stem and leaf plot that would have been much harder to answer from the original Table 10.3. For instance, judging from the stem plot, what was the approximate national average percentage of residents who are 65 or older? You can see that about half the data is above this and about half the data is below it. So I would say it's somewhere between 12 and 13%, perhaps 13%. Question 2, in how many states were more than 15% of the residents 65 or older? Well, more than 15% would be just 1, 2, 3, 4, 5, in 5 of the states. Which states were in the bottom 10th of all states in this statistic? Well, there are 50 states, so the bottom 5 would be these, and now we could look back up into the table and see which states those were. I know one of them is Alaska, which is this low figure right here. Finally, it asks us to consider the numbers 7.7 and 17.3 that are so far above or below the other numbers that they're called outliers. What could explain the two outliers? Well, I'm pretty sure I know the outlier 17.3, which is Florida, and that's because many people retire there. It's a place for older people to retire. The 7.7 for Alaska, I'm not quite sure of. It could be that it's an adventurous state where young people want to go when they're first setting out in life, but I'm not sure. There might be other reasons as well. Sometimes data is too closely clustered to help visualize trends and relationships. In this case, we can use a special type of stem and leaf plot called a split stem plot. Table 10.4 shows for quite a few states the amount of federal aid per capita to that state in dollars. To try to get some sense of this, we might imagine first breaking everything into groups of 500. So for instance, we could have data between $1,000 and $1,499, or 1,500 through 1999, 2,000 through 2499, and so on. Now we'll have two stems that are one which represents the 1000 through 1499 and one 1500 through 1999. Let's take a look. So the only figure that I see in here that's in the 1000 through 1499 is this one right here, and it goes in as a 1-4. The next one is the stem for amounts of money between $1,500 and $1999. We have quite a few in that range. I've filled in the second row. Let's take a look at the finished chart. So that's how you complete a split stem plot. Sometimes we can compare two sets of data that are related by viewing them simultaneously using what's called a back-to-back stem plot. Table 10.5 lists season totals of home runs for both Babe Ruth and Barry Bonds. We're going to put the two together in a side-by-side stem plot. I won't go through the steps in building the stem plot. It's the same as we've just done, but this time I want you to notice that the values on the right side of the stem increase from left to right, but the ones on the left side decrease from left to right. Let's take a look. The 5 lowest years for Babe Ruth can be explained by the fact that he started playing as a pitcher, and finally he didn't play much during his final year at all. Bonds missed most of 2005 season due to an injury. If we ignore those years, we see that Babe Ruth's home run totals were typically much higher than Bonds. Ruth often finished a season with 40 home runs or more. Bonds rarely did. So you could use this to argue that Babe Ruth was better than Barry Bonds. Another option that we have is to take our stem and leaf plot, in which we know that we can see the really big rows are the ones with the longest numbers of leaves, and convert it to what's just called a frequency table. And a frequency table, we just list the number of leaves for each item. We lose just a little bit of detail here. We don't see exactly how many home runs we got each year, but we do know that, for instance, in 3 different years, Babe Ruth earned between 20 and 29 home runs, and 7 years he had between 40 and 49. So a little less detail, a little more of just what's the overall result. If you enter the information from table 10.5 into list 1 on your calculator, set Xmin, Xmax, and Xscale to 0, 70, and 10, Ymin and Ymax to be -1 and 8, go to Second Stat Plot, and choose the settings I'm about to show you. Notice that plot 1 is turned on, and for type I have chosen this little thing that's going to be called a histogram. The X list is saved in list 1. Anyway, once I hit graph, I get the following. This is the bar chart corresponding to the frequency table. It is just called a frequency table. I'm sorry, this is called a histogram, which is the bar chart that corresponds to a frequency table. And you might find this useful in at least one of the homework problems, hint, hint. Anyway, once we have a histogram, it's got to have typically the same uh, horizontal gap for each of the different groupings. You don't have to do one grouping for each of the frequencies. You will often group them, like if there are 15 of them, you might group the first 3 and 4 through 6 and so on. The horizontal subdivisions of the x-axis must be equal, adjacent, and non-overlapping. Now we want to talk about describing the shape of such a graph. The shapes of histograms can be described many ways. Two of the big ones we're going to be talking about are modes and symmetry. A mode is an interval where data tend to cluster and to show up as longer leaf rows in the stem plot or higher bars in the histogram. Here's a look at a couple of possibilities. So again, looking for intervals where the data tend to cluster, we can see there's exactly one of those in 10.10a, but there appear to be two separate clusterings in 10.10b. We would say that the data in 1010a is symmetric because if we put a vertical line at the highest point and flip the graph over it, it wouldn't change much. It has symmetry about the middle line. Compare your memory of 10.10a, the nice symmetric graph, with these two graphs. And the one on the left has quite a bit of data extending out to the right of its mode, the high point, and we would say that the graph on the left is skewed right. Similarly, the graph on the right has a lot of data off to the left, so we would say it's skewed left. Looking at it, I might even wonder if that graph is bimodal because there seems to be a second slight clustering point for the data where we get to a height of 2. But if we just ignore that as an anomaly, then we would still say that graph on the right is skewed left. Finally, we consider time plots. If we use a line graph to track the value of some function against time, we are making a time plot. We see these in statistics quite a bit. I'm sure we've all seen time plots of the Dow Jones Industrial Average or the number of cases of COVID-19 worldwide. Table 10.7 shows total U.S. credit card debt in billions of dollars for the years 2004 to 2012. A time plot of it would look like the following. So no surprise here, you just plot the years as the X value and the billions of dollars as the Y value. From the graph, we can easily see that credit card debt was increasing from the years 2004 to 2008. And then from 2008 on, the credit card debt decreased, and in 2012 it had even dropped below the original 2004 value. By superimposing the graph of a set of related data, such as total student loan debt, on the same graph, we can see how the two interrelate. In this last graph, we can see that even though the nation's U.S. credit card debt has been dropping lately, student loan debt continues to climb. The only problem that I have with the last graph is I think it would be really nice to indicate that the greenish colored graph is the U.S. credit card debt and the red graph is total student loan debt. In other words, better labeling. Anyway, thank you very much for watching. You should now be prepared to complete Pearson Online Homework 10.2, due Friday at 10 p.m. I've added some instructor comments onto some of the questions to help a few of them that seemed a little bit ambiguous or tricky to me. And also I made a suggestion about using the calculator to do a histogram for at least one of the problems that might help you. Thanks and stay healthy.